Hello and welcome to some more physics revision with me, Will Carne.
And me, Connor Durkin. Today we'll be going through everything you need to know for an A-star in the A-level, focusing on the AQA course, but the topics may overlap with other courses, so hello to you all, you lovely people.
If you have any questions or comments, then you're very welcome to ask down there in the comments.
Not the description,
Not
onwards.
the description, right. Starting off with gravitational fields.
A force field is a region, force field, in which a body experiences a force. A gravitational field is an example of a field.
You can draw lines of force, or field lines, to show the direction of the force that masses would feel in the field.
The further away you are from the object, the less force you would feel, demonstrated by the sparseness of the field lines. Admittedly, this is an awful diagram, but you get the picture.
Yes, you do get the picture. Right, close to an object, like a planet's surface, the field is almost uniform, so the field lines are almost parallel.
The force experienced by an object in the gravitational field is always attractive, so that's very important. You may want to write that down.
For point masses, where the mass is concentrated at the centre, F equals G m1 m2 all over r squared.
G is the universal gravitational constant, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared, and where r is the distance between the centres of the two masses. This is called Newton's law of universal gravitation.
Because it's Newton's, a law, and universal.
That's quite universal films. We shouldn't.
Therefore,
F is proportional to the product of the two masses and inversely proportional to the square of their separation. The reason it is the square is that r is a radius, so the force is the same for both positive or negative.
it may also help to remember the formula for density, which is the mass divided by the volume.
Density. Gravitational field strength now. The gravitational field strength,
Yay!
G, is defined, little g, is defined as the force per unit mass, or G,
F over m.
F over m.
G is a vector, so that they have both magnitude and direction, always pointing towards the centre of the mass of the object whose field you are
The
describing.
value of G at the Earth's surface is approximately 9.81 newtons per kilogram.
G can also be seen as the acceleration of a mass in a gravitational field, or
The acceleration due to gravity.
point masses have radial gravitational fields, and the magnitude of G depends on the distance r from the point mass m.
You can get this using Newton's law of gravitation.
As gravitational fields are vectors, more than one can be added to find the resultant fields, and you know how to do that from last year, I believe.
I thought it said restaurant field, and now I'm hungry. Gravitational potential now. Gravitational potential V at a point is the potential energy the unit at that point would have, given by V equals minus gm over r.
Minus.
V is always negative and increases with the distance from the mass. Therefore, V, an infinite distance away from the mass, will be zero. Shown on the graph to be an asymptote to the x-axis. That's a fancy word.
Asymptote.
Yeah. Asymptotic.
Right, okay.
Asymptotic.
Yes.
The gradient of the graph at any point will give you minus g at that point, so you can deduce g equals minus delta v over delta r.
Yes, isn't that lovely?
Look at that little graph.
Isn't that
Actually
lovely?
quite cool. It's a very good graph. I commend whoever made that.
The gravitational potential difference
Is the energy needed to move a unit mass given by delta w equals m delta v.
where W is the work done, m is the mass, and V is the gravitational potential.
Given the gravitational potential, you can find the gravitational potential energy with, here we go, delta EP equals m times delta V equals minus g big M little m over r.
Yes.
Big M little m cut bucks.
The big M and the little m are just...
The two
They're just-
masses.
yeah.
The mass is the big thing, and the
It
mass
just
is the little
identifies which one is sort
thing.
of...
Big
yeah.
thing. Cardboard
Yeah,
box.
okay.
Moving on to orbits.
We love orbits.
Not the chewing gum.
And introducing our physics mascot, Trevor.
Trevor,
This
who
is
is
Trevor.
not at all related to anyone we might know in real life.
Right, but we don't have space for his body in this example, so it's just Trevor's floating head.
Dear Lord.
Right. A satellite is a smaller mass which orbits a much larger mass.
I think I had a dream about this once.
In a solar system, orbits are near circles, so you can use the equations of circular motion to describe
The
them.
centripetal force is
Very
the
quickly,
gravitational
before
force.
that goes
Ooh.
off, we need to talk about this. I don't know if for some strange reason, to get rid of the cat, we're saying that if the mass suddenly disappears, then it will go off at a tangent, which is the same as circular motion.
Yeah, if the forces disappear, it will go.
So we're
for
just
a
doing a
tangent.
little reminder of that.
Straight
Right.
line.
Yes.
No
Carry
other
on.
forces.
Centripetal force is gravitational force, therefore given by...
F equals mv squared over r, which is equal to g big M little m over r squared. Therefore, v equals the square root of gm over r, and therefore v is proportional to 1 over r squared.
That's very important. V is proportional to 1 over r squared, or inversely proportional to r squared. See, it's very important. You'll see. in a
Très
little-
important.
As speed equals distance over time, you can get V equals 2 pi r over t, and therefore t equals 2 pi r over v, and therefore equals the square root of...
4 pi squared r cubed over g big M.
Now that looks a bit complicated, but most of that is constant, so
Yeah.
you can just deduce that t squared
Pi's a constant.
is proportional to r cubed.
Pi is a constant.
Pi is a constant. That's why I said most of that is a constant.
So is G.
Yes.
And M.
M's not. Well, you could
it
technically...
is on that... well, does the Earth... moving on. Mass of the Earth, I don't know, or whatever
The
planet.
total energy remains constant, but the component's kinetic and potential energy can vary due to the orbit shape.
Geosynchronous satellites orbit directly over the equator, so are always in the same spot above the Earth. They orbit at the same speed that the Earth turns. Hence, the orbit will be one day with possible uses for communications like television and phone signals. And I have an issue with this little diagram we're showing here.
Yes, the Earth doesn't move.
The Earth doesn't move on that, so it's just like... Anyway.
Electric fields can be attractive or repulsive depending on the charge.
Electric charge Q is measured in coulombs C.
Opposite charges attract.
And like charges repel.
They do.
They do.
Right.
They do.
That's great.
If a charged object is placed in a field, it will experience a force. You can calculate the force using Coulomb's law.
Coulomb.
Which states that for the force of attraction or repulsion between the 2 point charges Q1 and Q2 in a vacuum is...
F equals 1 over 4 pi epsilon naught. Is that epsilon?
No, that's... Yeah, epsilon.
We should learn our Greek alphabet for this series.
Alpha. Moon unit alpha
That's your
and moon
constant.
unit
That's
zappa.
why I've separated it. Multiplied by Q1, Q2 all over r squared.
I think you're given that.
Where epsilon
That 1
naught
over 4 pi
is a
thing.
constant, which is 8.85 times 10 to the minus 12 not femto, it's force per meters, also known as the permittivity of free space.
Permittivity of free space is liberated space. The force on Q1 is always equal and opposite to that on Q2, and the law shows that the force is inversely proportional to the square of their separation. If it is not in a vacuum, then the force will also depend on epsilon thingy.
Right.
Thingy.
Electric field strength E is the force per unit positive charge, with the units being newtons per coulomb, given by E equals F over Q.
Where E is a vector, pointing in the direction that a positive charge would move. Electric field lines show the direction the force would act on a positive charge. Field lines point from positive to negative.
If a point charge has a radial field, then here E is given by the same constant again, multiplied by Q over r squared.
Where Q is the point charge and r is a distance from it.
This is another case of inverse proportionality, as E is inversely proportional to the square of the separation.
These graphs show that the difference is the first. Is it what?
These two graphs show that, and the difference between the graphs is that one is a point charge and the other... the second measures the strength to the surface.
That was badly written in the script.
Yes,
E in uniform fields, i.e. between 2 parallel plates, is given by F equals V over D.
Where V is the potential difference and D is the distance between the plates, as E is uniform throughout. And as you can see, if you ask to draw the diagrams, as you get to the end of the plates, then you can have slightly more bent field lines.
Bendy!
Because as it gets to the end, it will start acting more...
like a radial field rather than a linear field.
Yep.
It's very weird.
It's good.
Moving on to electric potential.
Yes, all points in an electric field have an electric potential given by...
V equals 1 over the constant weird thing, multiplied by Q over R.
Yes, where V is positive, Q is positive. Therefore, the force is repulsive.
Repulsive.
Where V is negative, then Q is negative. Therefore, the force is attractive. As R goes to infinity, the potential difference will approach 0.
Approach quite carefully, as 0 is quite a volatile number.
The gradient at a point on these graphs gives E. Therefore, E is the change in V over the change in R.
The electric potential difference is the energy needed to move a unit charge, and is given by delta W, change in work, is the equals Q times delta V.
Yes, that's it. Right, so we've done electric and gravitational fields, but there is a lot of similarities and one difference, I would say. And you need to kind of see the similarities. So it's time for a bit of a recap.
Recap.
Beginning with the similarities. There is charge instead of mass and different constants, but you can see the similarity in all these equations.
Just look at them.
Can you see that?
I can see it.
I can see that. You're just
Can you
swapping
dig
M's
it?
for Q's, really. And then
And G for the 1 over 4 pi epsilon 0.
Yes.
Look at that.
Other than that, it's pretty similar. G is a force per unit mass, E is a force per unit charge.
Newton's law and Coulomb's law give forces inversely proportional to the square of their separation.
Field lines are the same for a point mass and a negative point charge.
Potential energy per unit mass and the potential energy per unit charge.
The one big difference is that gravitational force is always attractive, whereas electric forces can be attractive or repulsive.
Very important.
Very important.
Very,
That's
very.
pretty much the only
Again,
difference. though.
très important.
Thank you. Okay, that's it for part 2. As we were doing gravitational electric fields, join us next time for the shortest video you'll ever see in your entire life, which is on the capacitance.
What about vines? They're pretty short.
Right, okay. Bye.